Good morning or good afternoon, ladies and gentlemen. My name is Alberto Sapora from Politecnico di Torino, and I'm going to speak about Mode 1 fatigue limit of V and U notches. Before starting, I would like to thank the other co-authors of this work, Professor Cornetti, again from Politecnico di Torino, and Dr. Campagnolo and Professor Meneghetti from the University of Padova. So when dealing with the failure behavior of brittle or quasi-brittle materials, two failure criteria are generally taken into account. The former is a stress criterion, according to which failure takes place when the applied stress reaches the tensile strength of the material, at least in one point, and this criterion works well for plane and notch specimens. The second criterion is an energy criterion, that is linear elastic fracture mechanics, according to which fracture happens when the stress intensity factor reaches its critical value, which is known as fracture toughness. And the criterion works well for a structure containing sufficiently long cracks. The analysis is limited here to mode 1 loading conditions, and I remind you that these criteria work well for the extreme cases cited above. Of course, problems arise in the intermediate cases, such as for elements containing short cracks, blunt or sharp V notches, also, or if we want basically to catch the well-known size effects. In order to overcome this drawback, different criteria in the framework of theory of critical distances were proposed in the past. We can distinguish between stress-based approaches, such as the well-known point method and line method, energy-based approaches, so the generalized or notch linear elastic fracture mechanics and quantized fracture mechanics, for instance, and coupled stress and energy approaches, such as, for instance, fine fracture mechanics. So since we are going to speak about fine fracture mechanics, we are going to implement fine fracture mechanics, just a few words on the criterion. So you can see here that there is a notch, so the stress field basically is generally a monotonically decreasing function after the notch tip. On the other hand, the stress intensity factor related to a small crack of length c stemming from the notch tip is generally a monotonically increasing function. And in this case, the coupled approach is described by a system of two equations of two conditions. The former is a stress condition, the second is an energy condition. So of course, both conditions are of average type. And at failure, the system, the criterion is described by a system of two equations in two unknowns. One is the failure stress, which is implicitly embedded in the stress field and the stress intensity factor function. And the other is the critical crack advance, which is a structural parameter since it is a function of the geometry and of the material properties through the characteristic length LCH. Now, what are the advantages of the coupled approach? Of course, it is more complex to be implemented since there are two conditions instead of one. But one of the advantages is related to the physical soundness, because in this case, both the stress and the energy principles are fulfilled. And this is, of course, if we implement, for instance, a stress-based approach, the energy criterion, the energy condition could be violated and vice versa. The second advantage is related to size effects. You can see here a 3-point bending test on a plane specimen. W here is the width of the specimen. And of course, for very small structures, when the crack advance approaches W, such as it happens for some smaller medical devices, you can see here that the coupled approach is the only one which provides a finite value for what concerns the failure stress, since predictions according to the line method diverge, since the stress resultant here over W tends to 0, and quantized fracture mechanics provides a vanishing failure load since the energy available along W basically tends to infinite. Finally, for more complex geometries, such as, for instance, interfacial cracks, or for particular loading conditions, speaking, for instance, of hydraulic pressure, the generalization of the coupled approach is very easy and easier than that related to other approaches. Fine fracture mechanics has been applied up to now mainly to static fracture. On the other hand, it was recently generalized also in the fatigue regime. Here you can see how the criterion can be expressed in the fatigue framework. For what concerns the material properties, we have to replace the tensile strength with the plane fatigue limit and the fracture toughness with the range of the threshold value of the stress intensity factor. And the characteristic length LCH becomes the threshold length LTH. Now, let us consider the first topic of this talk. So let us start from sharp V notches. Here you can see the geometry, basically. Omega is the notch amplitude, A is the notch depth, XY is the Cartesian frame of reference placed at the notch tip, and the structure is subjected to mode 1 loading conditions. And when dealing with sharp V notches, the notch stress intensity factor K1V represents the coefficient of the dominant term of the stress field ahead of the notch tip, of course. And according here, lambda are the classical Williams eigenvalues. You can find the values here tabulated for different notch amplitudes, whereas 1 minus lambda represents the power of the stress singularity. And according to the present definition, as I was telling, the physical dimension, the dimensions of K1V lie between those of a stress intensity factor, in the crack case, omega equal to 0 degrees, to those of stress, basically for their notched configuration, which coincide with omega equal to 180 degrees. So, within brittle structural behavior, K1V can be supposed as the governing failure parameter. So we can suppose that failure takes place when the notch stress intensity factor reaches basically its threshold value. Now, let us consider now an infinite or semi-infinite V-notched plate under tensile load. The notch stress intensity factor could be expressed in this way, where the shape function beta can be found tabulated in the literature. Of course, for edge notches, beta varies between 1.12 the square root of pi for omega equal to 0 degrees and 1 for omega equal to 180 degrees. On the other hand, if we wanted to implement the fine fracture mechanics approach, we need the stress field and the stress intensity factor functions, and we consider here these two asymptotic relationships. No problems for the first one. On the other hand, for the second one, here the parameters were evaluated, which are functions of omega, were evaluated by different scientists in the past, and here they vary from 1 in the crack case to 1.12 the square root of pi in the unnotched configuration. Now, we inserted these two functions into the fine fracture mechanics criterion, and we get basically two expressions. So we get the two unknowns. One is the threshold value of the notch stress intensity factor range for deep notches, and one is the critical crack advance, which are functions, as you can see, of the material properties and of these two functions, Xi and Psi, which are reported here, and which depend on the notch amplitude. Be careful that here Xi is depends on the criterion under investigation. So this expression holds for fine fracture mechanics, but if we implement another criterion in the framework of the theory of critical distances, we get a different expression for Xi, and the same for Psi, of course. Now, after substituting basically the failure condition, the notch stress intensity factor and its threshold value, we get the dimensionless fatigue limit, which of course, as a function of the notch depth, the dimensionless notch depth. You can see here, I repeat once more, Xi depends, as I will show you in the next slide, on the criterion under investigation, while beta are the shape functions related to the geometry. can see here the function C as a function of the notch amplitude. I remind you that omega equal to 0 degrees is the crack case, omega equal to 180 degrees is coincides with the unnotched configurations. And you can see here the Xi functions according to different criteria in the framework of the theory of critical distances. You can see here also that according to the present definition of the notch stress intensity factor, the point method, the Xi function according to the method is constant and equal to 1. On the other hand, this is basically the function, the Xi function related to fine fracture mechanics. And this is the psi function, so basically it's the crack advance according to fine fracture mechanics. So you can see here that in this case is a structural parameter. It depends on the notch amplitude omega. So if omega is equal in the crack case, you can see here, of course, the problem is failure is energy driven. So in this case, the stress condition only provides us the value for crack advance, which coincides in this case with that but the line method. On the other hand, for omega equal to 180 degrees, so in this case, the unnotched configuration, the problem, the failure is stress governed, of course, and the energy requirements provides the value for the crack advance, which coincides in this case with that by quantized fracture mechanics. And you can see here the dimensionless fatigue limit as a function of the dimensionless notch depth for different notch amplitudes. You can see here, of course, here the slope is negative and equal to 1 minus lambda. And note that here there are the shape on the x-axis, there are plotted also the dimensionless notch depth times the shape functions. So this basically can be applied to a generic infinite or semi-infinite geometry. And here is the zoom on this zone here with the intersection with the unitary y-axis. And here is the comparison between fine fracture mechanics predictions and experiments related to different materials and different knot amplitudes. So you can see here that basically the matching is pretty good. Of course, be careful that for finite geometries, all the relationship that we have proposed so far hold true, but for the shape function beta, which must be evaluated through a finite element analysis. So, of course, for finite geometries, the situation is a little more complex, but anyway, you can see here that the agreement is satisfactory. Now, let us consider now U notches. Again, the geometry is this one. A is the notch depth, R is curvature radius, and we are considering again mode 1 loading condition. If we want to implement fine fracture mechanics, we need the stress field and the stress intensity factor functions. Here we have considered these two expressions, the rather well-known relationship proposed by Krieger and Paris, and this is, which is probably less known, proposed by our research group in 2014. And in both expressions, it appears K1U, which is the apparent stress intensity factor, which according to Glinka can be expressed in this way, where Y represents the shape functions under consideration. And substituting, of course, these two functions into the fine fracture mechanics system, we get again a system of two equations in two unknowns. The former equation is an implicit equation in LC, and once LC is known from the first equation, we must substitute this into the second equation to get the dimensionless fatigue limit. Note that here we have introduced this parameter zeta A over R, which is known as notch equity. These are the results in terms of the dimensionless fatigue limit as a function of the dimensionless notch depth for different notch equities. And we have considered also the comparison with experimental results related, again, as you can see, to different materials and different works in the past. And the last slide is related to the crack advance here. in this case, again, you can see that the crack advance is again a structural parameter. You can see that for very small sizes, as the size as A decreases, the notch is equivalent to a long crack of the same size. And so the failure is governed by linear elastic fracture mechanics. So in this case, the stress criterion provides basically again the crack advance, which coincides with that by the line method. On the other hand, for very if A increases, so for very large A, the problem is the opposite. So the problem is stress governs, and the energy criterion provides the crack advance, which in this case coincides with that by quantized fracture mechanics. And that's the end of my talk. Thank you for your attention.